Welcome back, everyone. We are to chapter 6, module 6. We're going to be going through part 1 today, and today we're introduced to a normal probability distribution. Now, we've talked a little bit about normal distribution. Often we've seen this big shape, and we're going to see it a lot today, for the rest of the semester, actually. So a probability density function, also known as a PDF, that of course is different than a file that's a PDF. They just happen to have the same letters. A PDF is an equation used to compute probabilities of continuous random variables. It must satisfy two properties. The total area under the graph of the equation over all possible values of the random variable must equal 1, meaning all of the areas, this goes to negative infinity and to positive infinity, all this area under here needs to equal 1. Or 100%. The height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So the random variable is here. And all this is saying is that it's above the x-axis. It'll never dip below. In fact, it'll never touch the x-axis. It gets closer and closer and closer. These are called asymptotes. Example 1, you have a friend who is always late. Let x represent the minutes late and suppose, so this is minutes late here. Minutes late, and suppose all times between 0 and 30 minutes late are equally likely. So this is what's called a uniform density function, because it's uniform, meaning it's the same height all the way across. Making x equals 0 represents being there on time. So these are all the minutes that they're late. And so here's our uniform probability distribution. Same height all over the place. And this whole idea of area representing probability is going to be very, very prominent for the rest of the semester. So area is a probability. The area under the graph of a density function over an interval represents the probability of observing a value of random variable in that interval. So let's do our example here. And by the way, you'll notice here that the area is 1, so 0 to 30 means that the height is 1 over 30. So length times width, 30 times 1 over 30 is exactly 1. So we're going to use the same idea here. It says, what is the probability your friend will be between 10 and 20 minutes late? I want to point out that the distance here is 10 minutes. The height is still 1 over 30. This means that the area is 10 times 1 over 30, or 1/3, which is of course about 0.333. With the probabilities, we often go to 4 decimal places. Now we're going to go the other way. What if we're given the area, but we don't know how long they're going to be late? So they say, you're going to meet your friend at 10 a.m. You arrive on time. There's a 20% probability your friend will arrive in the next how many minutes? So we're going to work this a little backwards. So the area, which we know is 0.2, that's the 20%, is going to be equal to 1 over 30 times x naught. That's this length right here. Well, we're going to go back to our old algebra tricks, multiply both sides by the LCD, which is 30 in this case. And 2 times 30 is 6. So x naught is 6 minutes late. All right, that was a uniform density. They're not so interesting. The more interesting ones are maybe a normal density curve. So we can see our nice bell shape here. Properties of a normal density curve. It is symmetric around mu. That's the population's mean. The total area under the curve is 1. So all of the area, all the way from negative infinity to positive infinity, all this area here exactly equals 1, or 100% of the probability. The graph approaches but never touches the x-axis. So it looks like it's touching, but it's actually not. It's getting closer and closer and closer. There's a correspondence between the area under the curve and the probability. And we've seen this before. This is the empirical rule. One standard deviation out captures 65% of the area, and we'll learn where that 65% comes from today. Two standard deviations out, we're at 95%, and three standard deviations out, we are at 99.7%. All information we already know. So example 3. Suppose that the monthly charge for cell phone plans is normally distributed with a mean of 58 and a standard deviation of 15. Draw a normal curve with the parameters labeled. So if you recall, the mean goes in the middle. So the mean in this case is 58. And each of these ticks represents a standard deviation away. Standard deviation in this case is 15. So 58 plus 15. Here we're at 73. These are dollars. Plus another 15. We're at 88. These are obviously old cell phone plans. Plus 15. 103. Now we can go the other way. 58 minus 15. 43. Minus 15. 28. And minus 15. 13. And of course, as always, whenever you see me do something on a calculator, you should be doing it with your calculator as well. If I'm going too fast, you'll just pause it. Now, I don't know of a cell phone plan that's only $13. All right, so we drew the normal curve. We're going to shade in the region that represents the proportion of plans that charge less than $43. So here's the $43. The proportion of plans that are less is here. So we're shading it in. Doesn't have to be perfectly shaded. So there we are. It says, suppose the area under the curve, under the normal curve to the left of x equals $43, that's here. So they're claiming that this area here under the curve is 0.1587. And if we were to convert that to a percent, that would be 15.8, about 16% of the plans are less than $43. And we're going to interpret this. We would say that the proportion of cell phone plans less than $43 is 0.1587. Now, another way to word this is to say that the probability that a randomly selected cell phone plan is less than $43 is 0.1587. We can view it as a proportion or as a probability. Next up. Example 4. The lives of refrigerators are normally distributed with a mean 14 years and standard deviation of 2.5 years. Draw a normal curve and label with the parameters labeled. So we'll start, the mean is 14 years and standard deviation is 2.5, so this is going to be 16.5. Another 2.5 is going to be 19. Another 2.5 is going to be 21.5. Now, the x-axis in this case is in years. If I go down 2.5, that's going to give me 11.5. Down another 2.5 is 9. Down another 2.5 is 6.5. So we've labeled it. Shade the region that represents the proportion of refrigerators that last more than 17 years. So 17 is going to be about here. And more than 17 is going to be to the right. And 17 goes right there. And the third part is it tells us that the area to the right is 0.1151. So what we could say is that about 11.5% of the refrigerators last more than 17 years. Is how we would interpret that. Standardizing a random variable. Standardizing means that we are going to z-score it. And when we z-score it, we are converting the mean to 0, standard deviation to 1. So here we go, example 5. And we will need to use normal CDF in our calculator, which I'm going to show you. That we're going to spend a lot of time doing that today. And the formula is it's going to be the lower comma the upper, then the mean, then the standard deviation. Now, if it's already standardized, then we don't need to put the mean and standard deviation in necessarily. All right. So I'm not going to be able to draw every one of these, but let's at least draw the first one. So standard normal means that the mean is 0. And here they want area to the left. In this case, negative 1.5, negative 1.05. And the area to the left. So what we're going to use is normal CDF. And in this case, I'm going to put a big negative number. Because we're going from negative infinity up to, we can't actually put infinity into the calculator, up to negative 1.05. And then the mean is 0, standard deviation is 1. Let's see what that looks like. So I'm going to go to my distributions again, just like we did with the, and here we are. Now your interface may look very different than mine. So negative 99999. Your interface may look like this. We have to type in with the commas. Commas are above the 7. Above the 7 on this calculator. The upper boundary is negative 1.05. And the mean and standard deviation are here. Now, when we put this down, I'm going to notice this is most right down the middle. That's going to be 0.5, meaning 50% of the area is to the left. So this is going to be a lot less than 0.5, I'm guessing. Yeah. So this was 1A, 1B. Again, area to the left. So this is going to look like this. Normal CDF, negative 99999, because that's area to the left, up to 2.01. Now you can see 2.01 is way over here. So that's a lot of area to the left. That's going to be well more than 50% is my guess. Yeah. And we'll do 2A over here. And area to the right now of negative 2.01. Area to the right is all that. That's going to be a lot of area. Let's see what we have. This time, however, the lower is negative 2.01 and the upper is the 99999. see what we get. All right. Now it's negative 2.01. And now we want a big positive number. No. You'll notice it's the exact same value. As it should be, right? This was 2.01. This is also 2.01. One was going left, the other one's going right, so we get the same value. Right, yeah. 2b is going to be similar. So area to the right, so a normal CDF. And if you need to draw the picture every time, draw the picture every time, that's fine. And we are going to do 1.78 to 999. To a big number. As expected, this one's definitely smaller. Now 3a, I'm going to also draw the picture. This one's going to be a little different. We want the middle area between negative, negative 1.96 and 1.96. Almost 2, right? Negative 2 to 2. Remember, these are z-scores, so they're standard deviations. So plus minus 2 standard deviations. That should sound a little familiar. So it's the middle area. So we're going to go here. Negative 1.96, positive 1.96. This is where the 95%. Remember, 2 standard deviations out in both direction give us about 95%. This is where that comes from. So this is normal CDF, negative 1.96 to 1.96, so about 0.95. And again, now we can see where that comes from. Let's do 3b. So they want the area between negative 2.96 and negative 0.49. Negative 2.96 and negative 0. You may want to go through that page a couple of times with your calculator just for the practice. Make sure that you know when to do what, when it's going to the right, when it's going to the left, when it's in the middle. All right, moving on. Now we're going to go in the other direction. What if we have the area and we want to find the z value? So what we just did here was we were given the z value, find the area. Now we're going the other way. We have the area, find the z value. We're going to be using inverse norm. Now it's always area to the left. If it's not area to the left, we have to do 1 minus. You have to complement. Let's start with A. And I'm going to draw a picture for a lot of these. Remember, right in the middle, to the right or left, is 50%, 0.5. So it says area to the left is 0.2. So that means I want to be over here because that's less than 50%. So that's 0.2. And we're looking for this Z value down here. And so we're going to use inverse norm. Area to the left in this case is 0.2. That's all you need. The mean and standard deviation are 0 and 1. So now I'm going to go to distribution again. And inverse norm is right there. Area now, again, this says area to, it should say area to the left. Some of the calculators, you can change that, some of the newer ones, but I'm going to go as though we can't. Here we go. And notice it's a negative Z value, which is expected, right? I'm on this side of 0. Negative 0.84. We often just round Z values. This is a Z value. So negative 0.84. We often, or I round it off to 2 decimal places. And that's because of an old system where we used to have tables and stuff and we only had 2 decimals. Let's try B. And because it's area to the left, the setup is going to be the same. So our Z value that we're looking for is inverse norm of 0.8. And you'll note it's the exact same positive value of this. Right? 0.8 would mean it's over here. We have all that area. Positive 0.84. And you can see there's a connection. 0.2 that way, 0.8 that way. That leaves 0.2 over here. You're going to see a lot of connections like that. Let's save some space here. Let's try C. C is area to the right. Area to the right is 0.35. So because I'm going to the right, and this is 0 here, and we're less than 50% on this one, we're going to be in the positive over here somewhere. 0.35, less than 0.5. Now, so what I have to do to get this Z value, because it's area to the right now, and we only know area to the left, let's see that area to the left, then what we'll do is a little trick. We're going to do Z equals inverse norm of 1 minus 0.35. You just type it right in like that. So 0.39. So right there, 0.39. Here's the Z score, a Z value there. All right, let's try D. D says area to the right. So it's going to be similar setup to this one here. So Z is inverse norm. And 1 minus 0.85. So negative 1.04. And we knew that because area to the right is 0.35, 0.85, pardon me. That means area to the left is 0.15, which is much smaller. So that for sure is going to be a negative value there, Z value. All right, let's try E. Z scores that separate the middle 99%. We're going to get 2 z-scores for this one because the area here is 0.99. Remember, it's area to the left. So I want to be clear. If all of it has to equal 1, and the middle part is 0.99, that leaves 0.01. And half of that's going to go there. So we're left with 0.01. 0.001 is what we're left with, and I have to divide that in half. 0.005, same on this side. 0.005. Now, we do a lot of 0.05s. You have to have that extra 0 under 0.005 for this one. So area to the left here is going to be 0.005, no problem. Area to the left here is going to be 0.99 plus 0.005. We'll get to that. All right, so for this first one, we're at 0.005, and that's going to give us a negative value. Negative 2.57. Area to the left here is the 0.99 plus 0.005. So 0.99 plus 0.005. And it's the positive version, 2.57. And I should write that out. So for this first one, I'll call this z sub 1. This one would be z sub 2. So z sub 1 is inverse norm of 0.005. Z sub 2 is inverse norm of minus 0.005. All right. In F, I'm going to draw the picture out as well. They want the middle 95%. We kind of already know it should be something like -2 to 2. Standard deviations away. So the middle 95%, go here, here. Now what's left from the 95% is 5%, or 0.05. And to split it up again, I have to divide that by 2. So this area here .025. Area here is the same. And we're going to find these. Z sub 1 again. Z sub 2. Z sub 1. Inverse norm. Area to the left, that's 0.025. Negative 1.96, and Z sub 2, inverse norm, minus 0.025. It's the positive version. 1.96. And again, that's almost -2 to 2. So again, that's where we get that empirical rule of 2 standard deviations away gives us about 95% of the middle. So it's like way up there. All right. Let's talk critical value notation. This is Z sub. Now, in general, Z sub alpha is going to look like this. It's always the area to the right. That area is alpha. So I'm going to have to always put it in my calculator as 1 minus because, again, my calculator only knows area to the left. So this is going to be inverse norm 1 minus 0.01. .33. This will be inverse norm 1 minus 0.025. One minus 0.025. So for these critical values, it's always going to be the 1 minus 1.95, 1.96, pardon me. And the last one is going to be inverse norm 1 minus 0.05. One minus 0.05. 1.64. So it's not too bad. Just a few more. Now it can start to get a little confusing. Do I use inverse norm or do I use norm CDF? And so if we have the probability or the area, then we have to use inverse norm. If we have the z values, then we have to do normal CDF. So example 8, assume that the readings on thermometers are normally distributed with a mean of 0, standard deviation of 1 degree Celsius. A thermometer is randomly selected and tested. Draw a sketch and find the temperature reading corresponding to piece of 82, the 82nd percentile. This is the temperature reading separating the bottom 82% from the top. So let's draw our picture. The bottom 82%, that's going to be here. So this is 82. So we're looking for a z-score where we already have the area to the left. So this z here is going to be z equals inverse norm because we already have the percent. 0.82. And because that's bigger than 50%, that's for sure going to be a positive z value. So we get 0.92 degrees Celsius. Not too bad. So again, because we had the area, we're using inverse norm. Now, example 9 is a little different. Here we're given the z values and we're looking for the area. So this means that this area here is going to be normal CDF, negative 0.92 to positive 0.92, 0 and 1. We don't need that 0 and 1 because it's standard normal. So norm CDF, negative 0.92, positive 0.92, So 0.64, and we can see that that's a good chunk of all the area there. So it doesn't surprise me it's more than 50%. 6, 4. And our last one here, they give us the area. So now we're going to use inverse norm. Let's use a different color. Let's use green. So our Z in this case, remember, it's got to be area to the left. So they're saying that this area here is 0.8599. This is area to the right. So I'm going to have to do the 1 minus. You'll really need to get good at this. We use this function for the rest of the semester. So I'll make sure that maybe go through this video a couple times, practice it. I want to make sure that this does not slow you down on the test. Thanks.